So it's 11:15. Good morning to our very last session. Let's see, I think everything is online. There were only limited questions on Canvas, and I'm not sure about you, but I couldn't see them, and I'm not sure if that is just my account. But let me know if you could post your questions on Canvas or if it was also shown empty for you. So I couldn't see the questions there. I could download them, so I have done that, put them on a slide, and I will discuss the questions that I had there in a second. There's only 3 questions, so I will address those questions. And I have extra exercises that I can show you, so I will probably do that since we still have 2 times 45 minutes today. If you would like me to, we can also stop early. It depends a little bit on what your preference is. But if you have questions at this moment in time, if there is anything you would like me to do, put them in the live chat on YouTube, because that's something that I will be monitoring here. So also let me know if the questions of the week worked for you or did not. And I will address the questions that were there. But as I said, I couldn't properly see them, so I had to download them as a kind of text file. And I put them on a slide. That makes it a little bit easier to talk about them. So let's first look at the questions that people left there. So I'm going to switch to my iPad screen, which is here. So this is the exam a couple of years back. So that's how the midterm and probably also the final test would go in the old days, I would say. So last year and before that. So this is just students working in a lecture room on the exam. I think this is the midterm from a couple of years back. As you know, now it's going to be online, just like you had for the midterm. So the final exam is going to be very similar to how the midterm went for you. You may have seen that the midterm results have been posted on Canvas. Please check if your grade is as you expect it to be. There might be a difference between the grade that you saw in Canvas and the one that was in Ans Delft before, because I used a week for material in the test, so we compensated for that. So in principle, the Canvas grade should always be bigger or equal, larger or equal than the grade that was in Ans Delft, because the correction has been done in Canvas and not in Ans Delft. Also, from an organizational point of view, there is going to be the re-exam for the STAR test tomorrow, right? So tomorrow at 8 o'clock, you can redo the STAR test from week 1 if you like. And as you know, the STAR test is 10% of your final grade for calculus. Okay, so let's see the questions that I got via Canvas, and I don't see it changing on my screen here. So I'm not entirely sure if this is working out, and I cannot tell why. Let me, here it is. That just took a little bit longer than usually. So here are the questions that people left for me on Canvas before. So the first question is it true that sometimes only integration by substitution works and sometimes only integration by parts? That is true. So there are integrals that you can solve with either technique, but usually you have to choose one of the two and the other is not going to work. And it is not always clear beforehand which technique you should use. So maybe it's a bit of a trial and error here, and see where it gets you. So try to solve the questions that we gave you, and they should be sufficient preparation for the exam questions that you get. They are not very different from what you have seen before. It's along the same lines as the questions in the book and the questions in the homework. And as I already said, the questions in the old exams, so we put up old exams on Canvas. I hope you managed to find them. They are very representative for what you will be getting this year. So this year they're in the same line. Okay. And then the next question is, I try to solve the following integral for the online test, the integral from 0 to 4, 1 plus x over square root 16 minus x squared dx. And I kept getting that my answer was wrong. This answer is correct, and I've already reported that because I already got emails about it. So I have forwarded this question, and I've asked the people to change that in the online test. So indeed, this is the correct answer. Now, The next question, and this one was not typed as nicely as the previous question, but I think that the person who asked the third question meant to say, so how would you solve? Well, this is not really a question, but I think the question would be the integral 1 minus x in between brackets square root 9 minus x squared dx, probably. And if you see, that's actually the same question as the second one. So I am going to solve the second question here. So I will do the 1 plus x over square root 16 minus x squared to give the person from question number 3 the opportunity to do this by him or herself. So let us look at this integral here. So let's check that indeed the exact answer, the correct answer is pi over 2 plus 4, as Jana remarked on Canvas. So let's do this one. So I'm going to solve that. And for that, I'm going to input some fresh paper. Okay, that works. Excellent. So the integral we need to solve here, okay, is the integral, and let me check here, 1 plus x over the square root 16 minus x squared dx from 0 up to 4. Now, before you start working on this, you need to check if the integrand, so the function you're trying to integrate, so this thing here, basically the function you're trying to integrate is called the integrand. I used that name before. But you have to check whether this function is well defined at the two endpoints and also in between. So also for all the intermediate, for all the values of x in between 0 and 4 for this situation, but in general in between a and b, you have to check whether it is well behaved and whether it's defined. And you can immediately see that if you plug in x equals 4 here, we have division by 0. So this is an improper integral. For Dutch students, the translation for improper is oneigenlijk. And well, it basically means that something is wrong there. So something is not very good. So let's see. So what we have to do here is we have to replace the upper limit with capital R. So we have to do this. We have to take the integral from 0 to capital R, 1 plus x square root 16 minus x squared dx. And then I have to take the limit of R going to 4 from below. So the limit R is going to 4 from below. You could also write this as R is going to R superscript minus. We've seen both notations, right? And then you see, as long as R is equal to some number less than 4, so close to 4 but less than 4, then the integrand is well defined and we can immediately integrate here. It will turn out later that if you forget all about this and you just write a 4 there and you do everything with just 4 in the upper limit, everything's going to work fine. That doesn't always hold true. So you should be very aware of that it can be that you find something that doesn't exist if you plug in the upper limit. And especially also if you're integrating and somewhere along the way your function does not exist. So for instance, the tangent function, you know that the tangent function has a vertical axis, a vertical asymptote. If you're integrating over this vertical asymptote, well, horrible things can happen, and you don't see that. So if you integrate from 0 to pi and then the tangent and you just plug in the endpoint, everything's going to work out fine, but you find a completely wrong answer because the function is not defined along the way. So check that. Okay, now to do the integration, so let me do the indefinite integral. So I'm going to do the integration without using the limits for a bit. 16 minus x squared dx. Now, the crucial idea here is if you look at this integral is, well, you could think of substitution. So that would be one of the ideas that you can have, because there is a square root. I'm saying all things in between. So let me first write that down. Let's do this a little bit slower. So idea, integration by substitution. And, well, the kind of golden rule for integration by substitution is that you look at a complicated function, the square root in this situation, and whatever is under the square root, the argument of the square root, that's what you take. So here we would take u equal to 16 minus x squared. Now let's pause for 1 second. So before I'm going to look further into integration by substitution, we have also seen integration by parts. Could you do that here? Well, the reason I'm not going to try that is because when you're doing integration by parts, you have to differentiate and find primitives. Here in this situation of the square root, or even 1 over the square root, and that's pretty horrible. So I don't really like to do integration by parts here. So integration by substitution, that's what we will be following up on. And then if you have this u, then we know that du dx equals minus 2x. So du equals minus 2x dx. Okay. Now, if you look at the integral, then I see that there's an x here. So this x in the numerator could help me with this substitution. But there is also this 1 here. And that kind of makes this impossible. So what I'm going to do is I'm going to split the integral. So I'm going to say, well, this integral here equals the integral of 1 over square root 16 minus x squared dx plus the integral of x over square root 16 minus x squared dx. And then the idea is that for the second integral, plus, let's do this in red here. So the second integral here, that is where the integration by substitution is going to work. And the first one, there was no x in the numerator, so I cannot do integration by substitution. That's not going to work here. But that one looks a lot like an arcsine. So this one, you look in table of standard integrals. So that's the table that you get with the exam, the formula sheet. And then you see that this is going to be the arc sine of something. Yeah. So that's our plan. So let's see. I've got plenty of time. So let's solve this. And let's do these two integrals, because I think this is something that is important for the exam too. In the meantime, if you have a question, just put it in the live chat. I can see that on my screen here. And that's going to be the next thing I do. If I don't get questions in the live chat, I don't see anything there yet, then I'm going to look at examples that I have for differential equations, integration, and so on. But they are questions that you haven't looked at yet. So I think that's a bit less useful. I mean, it's interesting on how to solve them, but it makes more sense if I solve questions that you struggle with or that you have tried yourself, because then you see the difficult points in the question. So let's see. The first integral we need to tackle is the integral, let's do that in blue instead of green. The integral 1 over square root 16 minus x squared dx. Now, you could simply look that up in the table, but let's try to rewrite that to standard form ourselves. So I'm going to write that as a square root of 16 and then 1 minus x squared over 16. So just below the square root, I pulled out a 16 there, because the reason I do that is that I want a 1 here. Because I know the integral of 1 over square root 1 minus u squared du, that is an arc sign. So I'm going to write it as an arc sign of something, as the derivative of an arc sign of something. So this here is the same as, well, the square root of 16 is 4, so I'm going to write 1 over 4 in front of the integral. And then here I'm left with the square root 1 minus, and then I have x squared over 16, and I'm going to write that as x over 4 squared dx. And let's also put a dx here. Okay. And this one, if you look, this is the arc sign of x over 4, because if you differentiate that, you get precisely the integrand. And now with the chain rule, you would get an additional 1 over 4. So it's going to be 4 times plus some constant. And apparently it is simply arc sign x over 4 plus a constant. So that is the first primitive function, the first antiderivative. Next one, we have to do the integral in the red circle. So we have to consider x over square root 16 minus x squared dx. And we have already seen the substitution we need to do there. So let's also carry that out. And then we have that the integral x over square root 16 minus x squared dx. So I'm going to do the substitution. U equals 16 minus x squared. So du equals minus 2x dx. Let's all plug that in. So what we get is that we have minus 1/2 because of the minus 2 in the du. Integral, and then we get du over, and this becomes square root of u. And for this thing, I know a primitive function. This is u to the power minus 1/2. So it's going to be something like square root of u to the power plus 1/2. Now, if I differentiate that, I get the 1/2 here, but there is still a minus sign that I have to compensate. So minus square root of u plus c hat, say a different constant, some integration constant. And if I substitute back, then we get minus square root 16 minus x squared plus c hat. So the antiderivative for the whole integral is what I have here, plus this thing here. So let's write that down. And we find that the integral 1 plus x over square root 16 minus x squared dx equals arc sine x over 4 minus square root 16 minus x squared plus a new constant c tilde. So I had c, I had c hat. These constants are not interesting, so this one is, well, it's basically c plus c hat, and I call it c tilde, a new constant. I'm not interested in the constant. Then finally, we were interested in the integral from 0 to 4, 1 plus x square root 16 minus x squared dx. we have replaced that with the limit r is going to fall from below 0 to capital R, 1 plus x over square root 16 minus x squared dx. I have found a primitive function now, so this is going to be the limit r is going to 4, and then we have the arcsine function, x over 4 minus square root 16 minus x squared, and then in between x equals capital R and x equals 0. So almost done. Limit R is going to 4, and then we get the arcsine R over 4 minus the square root 16 minus R squared minus the arcsine of 0 plus the square root of 16 minus 0, which is 16. And then finally I can take the limit. So I get the arcsine of 1. So r is going to 0. I just replace r by 4 because, well, that's defined. There's no problem. And then we get plus 4, the square root of 16. And the arcsine of 1, so we need to find the angle that if I take the sine equals 1. So that's pi over 2. So we get pi over 2 plus 4. So this is indeed the exact answer to the integral. And I see that we have a couple of questions in the chat box, which is great. So Jana asks if you already had a 7 or higher for the STAR test. Is there a reason to do the reset? No, that is just practice. So there is no reason because, you know, if you scored 7 or higher, you get the full credits there. So it is like you scored perfect score for the STAR test. So you cannot increase your grade by doing the reset. It's just if you want to practice. If you say, well, I would like to do them again and see if I score higher, it's up to you. And Amber asked, why is du over square root of u? Maybe that the notation is what is confusing you here. So the question is this step here. So if you go from here to here, so let me add to this a little bit in red. So this here, the integral that I wrote, that is just a bit of shorthand notation that is the same as the integral 1 over square root of u du. So if you have 1 in the numerator, you can also write a du in the numerator. That's the same thing, it's just a bit of shorter notation. And this one, of course, you can do it. So this is the integral u to the power minus 1/2 du. And then the primitive for antiderivative is u to the power plus 1/2. And you have to write a 2 there and so on. But so if you have 1 over the square root of u du, you can write it as du over square root of u. That might be a little confusing. And Amber correctly answers the question of Jana. That's true. And then Thijs, yep, exactly. Thijs also gives the correct answer. Yep. So we are there. Excellent. So let's see. And Florine zegt, can you also take u equal to the square root of 16 minus x squared? Try it, I would say. That always is best to try to do it yourself. Try it and see what you get, and if you can get an antiderivative in that way. So I could do that, but it's really more educational if you try to do that yourself. This is not me being lazy because I'm going to do other questions anyway. But try it and see what happens. That's basically my message. So Puck says when I put in the answer in the online test, it says it is wrong. Yeah, so I had the same experience, and that was also the original question here. So Jana also got it wrong. I have reported that, so I hope it's going to be fixed soon. But it has been reported, and I emailed the person who takes care of the online tests there. So I had the same experience and tried it myself when somebody emailed me there, but apparently it's not been fixed yet. Now let me quickly go to some of the examples that I wanted to show you. I am going to check my email in a sec because indeed there is a question. So one of your tutors, Thomas, also tells me that the online test has a wrong question. So it has been reported, and I hope that it will be fixed. As you can imagine, everyone is very busy fixing the midterm grades, and also with the STAR test tomorrow again. And of course, we are also happily making up questions for the final exam. That's still quite far away for you. It's like the last day in the second week. I think Calculus B is a bit earlier. So Calculus variant 2 for the other guys. So I am going to do a couple more examples, but I have to look them up. So you have to give me a second here. So I have a collection of exercises. And as I told you, what I would like to do, so they're exercises for the individual weeks. And my suggestion is that I'm going to start at the very end, so with differential equations, because that's freshest in your memory. And also if we go back to week 1, hopefully now when you start studying, you will see that the first couple of weeks are kind of preparation. We're kind of getting the tools, notation, and functions that we need later on to do interesting stuff. So the first question that I wanted to tackle with you is a differential equation. Fixing my screen here to get a little bit larger. So example of a differential equation. Let's get some new paper. Okay. So say that we have the differential equation dy dx. Let's not write in red. That looks so aggressive. In blue. Dy dx equals minus 1/2 1 over square root 2 plus x y squared, and we also have that y0 equals 1 over 4 plus square root of 2. And the question is here, well, solve the differential equation. So what that means is find the function y of x. So apparently the differential equation, so prescribing the derivative plus the initial condition y0, that specifies one function y of x. During the lectures, we always wrote y of t, so we chose t instead of x. It's just a choice, right? You can choose your own variable names. So you see both, since usually, like when we're doing differentiation and looking at functions and drawing them, sketching them, we always have y as a function of x, or y is f of x. In differential equations, people often use t for time, but you can choose. So here, the person who made this question chose to write it as y of x. Now, in principle, differential equations, we have only seen one technique to solve them, so that's what you should try. we have only seen separable differential equations. And separable means everything with y to the left side of the equation, everything with x to the right side of the equation, and then try to integrate on both sides. So let's look only at the differential equation. And let's try to move all the y's to the left side. So then I have to divide by y squared. So we find, let me write this here as minus y squared over 2 times square root 2 plus x. Then do cross multiplication and we see that 2 times square root 2 plus x dy equals minus y squared dx. And let's now make sure that everything with y comes at the left side. So I'm going to write it as minus 1 over y squared dy equals 1 over 2 times square root 2 plus x dx. So now we have separated the differential equation. We have moved everything with y on the left, everything with x on the right, and we do integration on both sides. So we just put an integration sign and we say the integral minus 1 y squared dy should equal the integral 1 over 2 times square root 2 plus x dx. On the left, let's take a bit more paper. And let me copy the differential equation to, or basically where we were, let me copy that to the next slide. So I'm going to copy, go to a new page and paste, like that. And well, a primitive function for minus 1 over y squared, that is going to be 1 over y. Plus some integration constant equals, well, if you look a little bit here, you could do substitution, but maybe you can also see directly that the primitive is going to be something like the square root of 2 plus x. And if you differentiate this, you get precisely the integrand of the equation above, because we get 1 over 2 times the square root of 2 plus x, and that is precisely what it says. So this is a primitive function, and then we have an integration constant also on this side, so plus c2. So I can take these constants together, right? So I can say, well, that means that 1 over y equals the square root of 2 plus x plus c. And c is basically c2 minus c1, but I'm not interested in the values of these constants. So I just write c there, and I don't bother what it exactly is. So y itself is 1 over square root 2 plus x plus c. So this is the general solution of the differential equation. It is the solution if I only look at the differential equation. But here we also had an initial condition. So we also know the value of y at 0. So if I go back one slide, you see that apparently y0 equals 1 over 4 plus the square root of 2. So I'm going to use that. And let me go back to where I was. So here. So using this information, using the initial condition, I find if I plug that in, that apparently y at x equals 0 equals 1 over 4 plus square root of 2 on the one hand. And otherwise, if you look at the general solution here that we have just found, if I plug in x equals 0, then you see that it should also be equal to 1 over square root 2 plus 0 plus c. So apparently our constant equals 4, because then the two expressions are the same. So now we have all the information we needed, because this is y as a function of x, but there was still a constant in there, and now we have also found the value of the constant. So putting those two together, let me write that on this slide, because otherwise I have to copy everything again to make it more clear. So this combined with that, of course you should write that nicely on a fresh bit of paper so it's clear to read and you shouldn't go up and down. So we find that y equals 1 over square root 2 plus x plus 4. So that is the solution to this differential equation, and that is how you can do that. And as you know, at the final test, you have multiple choice options, right? So an alternative is that you say, well, I have this one. So I have the original question. So this is the question that you're being asked. And I need to find a solution. What you could also do is look at the multiple choice options and see which one satisfies the equation. So which one has this property and which one has this property. And only one of the options is going to satisfy both of them. So that will be an alternative approach, which is entirely correct. It is likely not what your tutor or the person marking your exam thinks that you will do. So you have to explain carefully what you do there. But if you say, well, I pick option C or whatever, they are random, you get them in different order. Each of you gets them in different order, different numbers and so on. But to say option C satisfies both the initial condition and the differential equation, so that is the solution. That is mathematically entirely correct. And then if you're going to do that, so you can first try solving it, but if you somehow don't manage, first look at the initial condition, because that is easiest to check. Here I have to differentiate and maybe compute something complicated in the right hand side. But the initial condition, so if you plug in x equals 0, t equals 0, that is easy to find, of course. So you can quickly eliminate some of the options maybe there. Okay, let's do one more differential equation. So I have a few of them. Let's see. Here is another one. Yep. So let me also. So the questions I'm doing here are not from the book, and you probably haven't seen them before. There's just a couple of extra ones. So dy dx equals minus 3 times 1 over 3 plus x squared y to the power 2 thirds. And additionally, y0 equals 343 over 27. Okay. So what does it say here? Well, let's write this a little bit easier maybe. This is minus 3 y to the power 2 thirds over 3 plus x squared. So I am going to do cross multiplication, and then we see that 3 plus x squared dy equals minus 3y to the power 2/3 dx. Everything with y to the left side of the equation, y to the power minus 2/3 dy equals minus 3 over 3 plus x squared dx. Let's now integrate on both sides of the equation, because the left side only depends on y and the right side only depends on x, so I can do the integration. So integral y minus to the power 2/3 dy equals integral minus 3 over 3 plus x squared dx. Well, the left side is easy to integrate. So that is y to the power, and we add 1, so we get 1/3. If you would differentiate, you would get an additional 1/3. We don't want that, so I write a 3 there, plus some integration constant, equals, you can do substitution here, u equals 3 plus x. Actually, let's do that. So let me just copy the integral for a sec. 3 plus x squared dx. And I'm going to a new bit of paper. Copy the right hand side here. Copy. New page. And there it is. So I'm going to use substitution. And I am going to choose u to be 3 plus x. Because in the numerator I have something squared and something is difficult, so I'm going to choose that. Well, then du dx equals 1, so du is dx. So it means, if I call this integral capital I, it means that capital I is the integral minus 3 over u squared du. So primitive is u to the power 3, u to the power minus 1, of course, sorry. And the minus 3 we keep here, but it becomes a plus 3 plus c2. So if you differentiate this, you get the minus sign, so minus 3 times u to the power minus 2, so that's precisely what we want to have. And let's plug in x again, so we have 3 over 3 plus x plus c2. Okay. Now on the first page we had 3y to the power 1/3 plus c1, and that apparently equals 3 over 3 plus x plus c2. So I can rewrite that a little bit, and I can say that apparently y to the power 1/3 equals, so I'm dividing by 3, moving the c1 to the other side, and then we get 1 over 3 plus x, because I've divided by 3, and I'm just going to say, well, a new constant. So I could express this in terms of c1, c2, but why would I do that? Because it's an arbitrary constant, I'm not interested yet in that value. So y itself is the whole expression to the power 3. So what you see here is that this constant c, we still need to determine it from the initial condition, so from the value of y at x equals 0. But you see that it is in the formula inside the brackets to the power 3. So sometimes students forget about these integration constants. They don't write them at all. And then at the very last moment in time when everything is finished, they write plus c. But it doesn't work like that. That is incorrect. So you have to do it at the proper time, like I did here. So what you sometimes see is that students, well, they just find this here. And then from that, they do it to the power 3. And then at the very last moment, they write plus c. But that's not correct. So when you do an integration, that's where you write an integration constant. So we're almost done. So I have, on the one hand, found by solving that apparently y equals 1 over 3 plus x plus c to the power 3. On the other hand, I have the initial condition, which read 3, 4, 3 over 27. So if I combine those, I find that 3, 4, 3 over 27 should equal 1 over 3 plus 0, because x equals 0 in the beginning, plus c to the power 3. Now, hopefully, you see that the numbers are chosen in such a way that you get relatively nice numbers. And 343, that is 7 times 7 times 7. So if you take the cubic root, you find that 7 over 3 equals 1 over 3 plus the constant. Let's write it a little bit clearer, 1 over 3. So apparently c equals 6 over 3, which is 2. So the conclusion is y equals 1 over 3 plus x plus 2 to the power 3. So that is the solution of this differential equation. So I see that it's 11:30 and a bit. So let's have a little coffee break. If you want me to do any questions, I've got a bunch of them, so I can keep on giving you examples here. But if you have questions, put them in the chat box. And I'm pointing towards my screen because I see them there. And I'll treat those first. So let's have a break, get some coffee, use the bathroom, and then I'll see you in a bit. let's start again. It's 11:45, and we've got 45 minutes left, and then all calculus lectures are done for the term. So during the break, there was a question on Canvas, which I copied here to the slide. Let's see, can I move this? No, whatever. So it says, in the lecture from week 7, there was this question of a cable hanging between two poles 6 meters apart, and what is the length of the cable? And in the solution, how did you directly find fx equals 3 times cosine hyperbolic x over 3? That would be given. So if we would ask you this question, then we would tell you that since it's a cable, that the form it assumes is this catenary. So this is all related to catenary. There's quite a number of Dutch students. So in the Dutch language, this is called ketting. A lijn, one word. So ketting is chain and lijn is line or curve. So it is the form that a chain assumes if you only support the two endpoints. And that is a given, so you don't have to know where that comes from. You can do that using physics and using the forces in between that hold in a cable, in between the parts in a cable. But that is not in this course. So in this course, it's just assumed that a chain has this shape. And the general shape, as we have seen, is that y is some constant a times cosine hyperbolic x over a. And then if you let x, for instance, vary in between minus a and a, then you have a chain there, a chain shape, which looks a little bit like a parabola, as we have seen in the lectures. So this is a given, and this is something that you can use and will be given to you. Then it says here also in the book there is a more general equation for catenary, a times cosine hyperbolic x over b, and then find a and b to match it. That is actually a different shape, so that is not a catenary shape, so the book is a bit wrong there. But here also you just have to plug in those values. So if you look at the question from the book, it is basically, they said, well, here you have the same a, and that is precisely the shape that you should have. And this is going to be a different shape. So if you would plot this for a and b different values, then you get a different shape there. And of course, the way to solve that, I'm not sure if you want to know or if you had any difficulties with that, is it says here the ends are 40 meters apart and have a height of 20 meters. The height in the middle is 10 meters. So you just have to draw a little picture there where you input this data. And then if you plug it into your formula, so the shape that you have here is something like, what is it? Y equals a cosine hyperbolic x over b. Then from the data it follows that, let's see what it says, the height in the middle is 10 meters. So that means that here you have 10. The ends are 40 meters apart. So that means that we are at 20 and minus 20. And have a height of 20 meters. So that means that if you look at the, I should make that a bit bigger, but here apparently we have 20. So what we have is that y for 0 equals 10 and y for 20 equals 20. So y0 equals 10, that gives that 10 is a times cosine hyperbolic 0, and the cosine hyperbolic of 0 equals 1, so that's just 1. So we have already found a here, apparently that's 10. And then we also have that 20 is a times cosine hyperbolic 20 over b. And this can give you b. Actually, I would like to show how this goes, because it is a trick that you should have seen once. And I'm not sure if you did any questions on that. So where we currently are with this question is that we have a times cosine hyperbolic 20 over b equals 20, and we have found that a equals 10. So apparently the cosine hyperbolic of 20 over b equals, well, 20 divided by 10 is 2. And then it makes sense to go to the definition of cosine hyperbolic. So that's the exponential of 20 over b plus the exponential of minus 20 over b divided by 2 equals 2. And now the main idea, and this is something that you would not easily come up with yourself if you have not seen that. So the trick is here to introduce a new unknown, let's call it z, is e to the power 20 over b. And an important thing to note here is I introduced z as an exponential function of something. And we have seen that the exponential function, well, for x going to minus infinity, it goes to 0. And then it increases, and it goes up, it grows exponentially. So it's always positive. So z should be a positive number with this definition. So what do we have now? We have that z plus 1 over z, the whole thing divided by 2 equals 2. So z plus 1 over z equals 4. And this is still a bit of a strange equation because it has 1 over z in there. We don't have any easy techniques how to solve that. But what you can do is multiply the whole thing with z. Z is a positive number, so that's okay. And then we find that apparently z squared plus 1 equals 4 times z. And now we're getting somewhere, because this is a quadratic equation, and for quadratic equation you have the ABC formula. You know how to solve that. So let's also do that. So we have z squared plus 1 equals 4z. So z squared minus 4z plus 1 equals 0. I didn't prepare this question, so if I make any errors, please forgive me. So the solutions z1, 2 are, well, minus b, so that's going to be 4, plus or minus the square root b squared, so it's going to be 16, minus 4 times a times c, so that's simply 4, divided by 2a, which is 2. So we find 4 plus or minus the square root of 16 minus 4 is 12. Is 4 plus or minus 12 is 4 times 3. So that's going to be 2 times the square root of 3 over 2, which is 2 plus or minus square root of 3. So something interesting happens here. I'm going to find two solutions, and hopefully you remember, we've seen that, but maybe you also know that the square root of 3 is approximately 1.7. So both of them are positive. Both of them are valuable solutions. Now z was introduced here to be the exponential of 20 over b. So apparently z is the exponential of 20 over b. So that is the same as 20 over b is the ln of z. So that means that b itself is 20 divided by ln z. Now z is 2 plus or minus square root of 3. So it seems that I find two different values for the b here, which is a bit strange because there was only one curve going there. So what's happening here? Let's see. So we have, let's put the 1, 2 here. So then we have that b1, 2 is 20 over ln z1, 2. And well, what I basically have found now is that the shape, so originally we were talking about the shape of a function here. So we were interested to find this function y. We immediately found a to be 10. And now for this b here, I find two different values. So something funny is happening there. And what I wanted to show you is that we are basically going to find the same curve but two different formulas for it. So we have that y is 10 cosine hyperbolic x over b, and b is 20 over ln 2 plus or minus square root of 3. So let's pick this one. So then we get x over b, so that's going to be x times ln 2 plus square root of 3 over 20. So that is the same as 10 times e to the power x times ln 2 plus square root over 3 over 20 plus e to the power minus x times ln 2 plus square root over 3 over 20, and the whole thing divided by 2. Okay. Now what I would like to show you is that if I would have started with the minus sign here, I would get a minus sign there, and I would get a minus sign there, and I would get a minus sign there, is that this is basically the same. And the way you can see that is that if you have minus ln 2 plus square root of 3, that is the same as ln 2 plus square root of 3 to the power minus 1, because if you have a number in front of the ln, you can write it as an exponent. which is the ln of 1 over 2 plus square root of 3. And as you know, you can do a kind of trick to get the square root out of the denominator. Let me just do this, because otherwise it looks a little bit like there is a square. I'm going to do some more paper. So what we have found is that minus ln 2 plus square root of 3 is the ln 1 over 2 plus square root of 3. That's what we had on the previous slide, which is the ln 1 over 2 plus square root of 3 times 1. And 1 I'm going to write today as 2 minus, like this. And this is the ln 2 minus square root of 3 divided by 4 minus 3. So 2 times 2 minus square root of 3 times square root of 3. So that equals the ln 2 minus square root of 3. So having this, and going back to the previous slide, so this is just a couple of intermediate steps, but if you look now to the equation that we found for the shape, you see that if you do these replacements, basically they end up giving you an extra minus sign in front of the argument of the exponential. And if I would have taken the other b here, then the plus and minus sign just swapped. So this is a very long explanation and computation just to tell you that whether you take the plus or the minus sign, it doesn't matter. So either you get a plus sign here and a minus sign there, or the other way around. So that is the motivation here. So at the exam, what you could do if you have a question like this, you could say, well, I'm going to take just, for instance, this b here with the plus sign, and if I would take the minus sign, I would get the same solution. So you could do it like that. Okay, so quite a long solution to this problem here, but hopefully this made it more clear. A bit messy, but I didn't prepare it. It was a question just asked. And in the meantime, in the chat box, Amos says, can you also use cosine cosine hyperbolic inverse to calculate this? In principle, that's correct, but we didn't talk about the inverse of the cosine hyperbolic function. So there is something which is called arc cosine hyperbolic, just like you have an arc cosine, arc sine, etc. There's also arc cosine hyperbolic. But since we didn't do that, you would have to give this solution, so in terms of ln's and so on. And then, Janne, how do we know the primitive function of the arc cosine? The derivative. The derivative. So the derivative of actually, it is nice because I am going to find a primitive for the arcsine function. If you look, when we talked about arcsine, arc cosine, we also looked at derivatives, and one just has an additional minus sign. So that's why only one of them is listed in the table. So if you look it up, you will see that this derivative of 1 over square root 1 minus x squared, that one. 1 is the arc sign, and if you put a minus sign there, you get the arc cosine. So that's why it's not in the list there. So let me go back to the examples, because at the moment all the questions have been answered. I am going to do a few integrals. And let me do the one first that is kind of inspired by what we have just seen. So the first one that I would like to tackle, it wasn't really Janne's question, but it made me think of it, is the integral of the arcsine function. Now, if you look, you would expect this maybe to be in the list of standard integrals, like, well, we know the sine and the cosine, we know the primitive functions, but here we do not readily have a primitive function. Substitution is not going to work here, right? You're not going to have anything useful there. So what we are going to do is integration by parts. So I'm going to choose u to be the arcsine function. I'm going to say that dv is dx. So with these choices, you find then that du dx is 1 over square root 1 minus x squared. So du is 1 over x squared dx. And for v, you can choose v to be x. So you can choose how you remember the formula for integration by parts. So let's say u dv equals uv minus integral, and then they swap around, v du. So if I call my integral that we're trying to compute capital I, then we find that apparently capital I equals, well, x times the arcsine function, that's uv. So x times arcsine x minus integral v, that's x, du 1 over square root 1 minus x squared dx. And that is quite nice, because now, if you look, I can do integration by substitution here. Because I have a 1 minus x squared, the square root of 1 minus x squared, so I can do the substitution, u equals 1 minus x squared. So different u from the one we've just seen. So let's do that. So let us compute separately the integral x over square root 1 minus x squared dx. So this is going to be I2. So this one I do with integration by substitution. And I'm going to do u is 1 minus x squared, then du is minus 2x dx. And we find that apparently I2 equals integral, and then we have minus 1/2, I write that here, 1 over square root of u du. So the primitive here is minus square root of u plus some constant, which is apparently minus the square root 1 minus x squared plus some constant. So the conclusion is that the full integral, so the integral of the arcsine function, is what we had on the previous page, which was x times the arcsine and then it was minus I2 if you would look back on the previous slide. So we find x times the arcsine function, then we get plus square root 1 minus x squared plus c tilde. C tilde is a new constant, minus c here, but I'm not interested in the precise value. So this is a primitive function for the arcsine. So using both integration by parts and integration by substitution. And that was kind of inspired by Jana's question in the chat box. So let me do another one. using one of the integration techniques we have seen. And I think you can do this one using both techniques. So let us consider the integral x squared 1 plus x to the power 37 dx. Now, in principle, you could, this is a polynomial, and for a polynomial it's easy to find a primitive function, but then you would have to expand 1 plus x to the power 37, and that doesn't make sense. That's way too much work, and you cannot really do that. Likely you can also do this with integration by parts, but you can also do the substitution. So I'm going to do that because I think it's simpler. So integration by substitution. And what I am going to be using is u is 1 plus x, because then this 1 plus x to the power 37 is going to be u to the power 37, which is a lot nicer. So du is dx. And then our integral, well, there is one problem, because in our integral here, so this is nice, this is going to be u to the power 37. This thing is going to be du, so that's also nice, but there is still an x squared here. So the way you can do that is that you say, well, from this choice, I have that x equals u minus 1, which means that x squared is u minus 1 squared is of course u squared minus 2u plus 1. So now we've got all the bits and pieces. If we call our integral capital I, then we find that capital I is the integral. Well, the x squared I can replace with u squared minus 2u plus 1. Then I get u to the power 37 du. And now it makes sense to expand this. So this is the integral of u to the power 39 minus 2 u to the power 38 plus u to the power 37 du. And of course we can readily integrate this. So this is 1 over 40 u to the power 40 minus 2, and this is u to the power 39, 1 over 39, and then finally plus u to the power 38, 1 over 38, plus some constant. And then finally you can replace u by its definition. So u equals 1 plus x. And I'm going to do that the lazy way. So I'm going to replace u by 1 plus x. Going to replace this u by 1 plus x. And finally the last one, I'm going to replace u by 1 plus x. And that is the answer to this integral. So integration by substitution with a little twist, because there was still the x squared and we had to write that in terms of u as we did here. So that was a little bit extra. And as I said, you can also do this with integration by parts. If you prefer it, if you think it's a nicer technique, you're welcome to use that too. So as I've told you before, if you do something in a different way than expected, but you do it mathematically correct, you will get full score during the exam. But always try to make very clear what your thought process is and which techniques you're using. That helps a lot. So let's see, I'm scrolling sample problems. I think I'm going to leave the integration for a bit now. also have during the lectures. So there is only so much time. So I'm looking at a nice problem of something that maybe we haven't seen yet. Okay, let's do here. Let's do an example of implicit differentiation. So the question here is, we have a curve. And the curve is given by sine x squared y squared plus x to the power 3y equals x squared minus 4. I am quiet because I get some messages from YouTube. But I think all is okay. So the way you should look at such an equation for a curve is not that you need to solve x as a function of y or y as a function of x. This is just some formula, and if you choose a certain y value, then likely you find x values such that this equation holds. And if you would take all the points x and y, you get a curve. So I'm not sure what this thing looks like. I haven't got a clue. But if you would, in an xy plane, draw this, then you would get some kind of, so I'm just choosing something, some kind of curve C. So every point xy on this curve satisfies the equation. So if you would plug the x and y values into the equation that I just wrote down, it should solve it. It should be a solution of that. Okay. And then the question is, so say that we pick a point, so some point here, P, compute the tangent line. So there should be a tangent line L, so find that. So in particular for this question here, we are being asked to find the tangent line at 2, 0. So the point does not correspond to my picture, but there is a point on the curve. Apparently 2, 0 is on the curve. You can easily check that. So if we plug in y equals 0, this one becomes 0, this one becomes 0, which means that x squared minus 4 should be 0. And indeed, if x equals 2, that's 0. So this is a point that is on this curve that I drew here, on the red curve. And the question is, find the tangent line. So for the tangent line, we need to know the slope. So L, y is mx plus b, and m is dy dx for x equal to 2. So that's one of the things that we should find. And the other thing that we can use that the point 2, 0 should be on the line. So how can we do that? Well, we are going to use implicit differentiation. Implicit differentiation. So what I'm going to do is replace y by f of x in the formula. So I'm going to write it as sine x squared fx squared plus x to the power 3 fx equals x squared minus 4. And now I am going to differentiate this whole expression with respect to x. So I'm assuming that locally close to this point P, I can write y as a function f of x. So the sine, if you differentiate that, you get the cosine. So then we get, so differentiate. Then we get the cosine x squared fx squared. Chain rule, so I also have to differentiate x squared fx squared. So that's going to be times 2x fx squared plus x squared. Derivative of fx squared is 2 times fx. And then with the chain rule, we get an additional f prime x. And then I have limited space here, but I'm still going to squeeze it in. So the derivative of x to the power 3 is going to be plus 3x squared fx plus x to the power 3. And then I have to differentiate f, so that's going to be f prime x equals 2x. Okay. And now in this equation, I have to plug in, so let me do that on a new page. Let me copy the equation like this. So I'm going to substitute x equals 2, f2 is y equals 0, because the point where I would like to find the tangent line was the point 2, 0, x equals 2, y equals 0. So if you do that, then you find that the cosine 4 times 0 times, so we get 2 times 2 times 0 squared plus 4 times 2 times 0 times f prime 0 plus 3 times 4 times 0 plus 8 f prime 0 equals 2 times 2 equals 4. So a lot here drops out. So we get the cosine of 0 is 1 times 0 plus 0 plus 8 times f prime 0 equals 4. So apparently f prime 0 equals 4 over 8, which is the same as 1 over 2. So now we have the slope of the tangent line. And then I also know that the point 2, 0 should be on the line. So if you plug that in, then you see that 0 equals 2 times 1/2, or let's swap them the other way around and it's immediately clear where they come from. M equals 1/2. Oops, that's not what I meant to do. 1/2 times 2 plus b. So apparently b is minus 1. Sorry for squeezing that in here, but what we have found now, I don't want to start a new page because we're almost done, is that apparently the tangent line is y is 1/2 times x minus 1. So that is how to do a tangent line to a curve. You would use implicit differentiation. So you're not going to try to write y. You're not going to solve for y and write it as a function of x, but you're going to differentiate the whole equation for the curve, and that makes more sense. And it's sometimes the only way that you can actually do this. Okay. So I am going to stop at this moment in time. If you have any further questions, please let me know. So just email me as before, write your question plus make a photo of what you try to do there, and then it's very easy for me to react to that. Prepare well for the exam. Try to do as many questions, as many practice as you have. So all the questions from the book, from the homework, the old exams, they're all great preparation. The online tests, the online practice, do all of them. If you run into any difficulties, please let me know. And maybe it's also a very good idea to try and solve the old exams together with friends, because you can help each other. So this brings me to the end of the course. I hope you have enjoyed it at least a little bit, even though mathematics may not be your prime interest. So prepare well for the exam. I hope you all do well. You really should do the exercises. So if I'm doing them here, it probably makes sense if you try to do them yourself. It's a whole different matter. So please practice, and I wish you very good luck with the exam, and I hope to see you in some bright future in real life at university. Say hi if you meet me there. Okay, bye.